Alright, remember that Faraday's experiments indicated that magnetic fields create current when the amount of field inside the current loop changes. We'll need to formalize that somewhat so to make quantifiable predictions. We'll begin with an analogy. Imagine you have a fan pushing out a steady stream of air, and you also have a rectangular loop of metal. The air holds a net or filter, and you're interested in maximizing the amount of filtration done, that is, the number of particles pushing through the net. How would you arrange the loop relative to the fan? And of course, you'd do it edge on to the fan, right? More like this than like this. Holding a loop so its perpendicular airflow clearly maximizes how much air passes through it. Spinning in any amount reduces that airflow all the way to zero for a loop parallel to the flow. Figuring head on makes it clear why. We're reducing the apparent cross-sectional area, even though not changing the actual area at all. We do the same for magnetic field, where the field lines take the place of the airflow. We define the direction of the area of the loop as a direction parallel to the axis of the loop. We can increase the amount of field passing through the loop by increasing the loop area, or by increasing the field strength, or by increasing how much they align. We define the magnetic flux as the product of the field strength with the effective area of the loop that it's piercing. The effective area is in this case, A times B times the cosine of the angle between them, because that's how long this side is. So the flux, represented again with Greek letter phi, is the effective area times B, which is the area times the field strength times cosine angle between them. The units are called the Weber, where 1 Weber is 1 Tesla meter square. Current is induced in a current loop whenever the magnetic field flux through the loop changes. That is, not by how much is there, but how fast it's changing. Direction of current is in the direction that would produce a magnetic field opposing the change in flux. This is Lenz's law. Lenz's law says that you induce a magnetic field so as to produce flux that would reduce the change in the flux, trying to preserve its value. So if the flux is increasing, the current flows to create a magnetic field the other way, reducing the increase in flux. And if the flux is decreasing, the current flows in such a way as to support the flux, to restore it. It's also important that we'll find out that Lenz's law means there's always less of a change by Lenz's law than you originally had. So it will not win, but it will always resist this change. For instance here, as the magnet descends, the flux through the loop increases. Lenz's law says the induced current would create a magnetic field that points upward, so to reduce how much the flux increases by. The current would flow counterclockwise as viewed from above. So here, in what direction will the induced current flow? All right, so the first thing we should probably do is figure out which way the field's actually moving or pointing. Remember that fields point from north to south, so they look something like this. This is a classic dipole field, which hopefully is now getting very familiar to you. So something like this. So we can see that the flux is directed upward through the loop, but as the magnet gets further away, that field gets weaker. So the upward flux is getting lesser. We need to create a current that will give us more upward flux, i.e. a field pointing upward, which if we look at here and we do our right-hand rule would be direction A. Current has been flowing in the top circuit for a long time. Now the switch is opened and the current stops. What direction is the current induced in the lower circuit? In the same sense, the opposite sense, or no current? All right, the top circuit creates a field that is pointing upward at the location of the lower circuit. But when the switch is open, that field gets weaker, which decreases the flux through the lower circuit. The induced current is going to shore up the flux, so it needs to generate a field that points upward, which means the current must be in the same sense. What is the sense of the induced current here? Counterclockwise, counterclockwise, or there's no current? All right. The field from the wire at the location of the loop is into the page. As the loop gets closer, that field gets stronger, so there's more flux into the page. The induced current will produce a field that opposes the increase of inward flux, so it must point out of the page. And to produce a field out of the page, the current must be counterclockwise. As a coil moves to the right at constant speed, it passes over the north pole of a magnet and then moves beyond it. Which graph best represents the current in the loop for the time of the motion? A counterclockwise current is viewed from above the loop is a positive current. A clockwise current as viewed from above is a negative current. All right, here, when we're on the left of the magnet, still approaching the magnet, the flux is increasing as the field gets stronger. The induced field must point downward, so the induced current must flow clockwise. Our convention says that that's a negative current. On the other hand, as the current loop leaves the magnet, the flux is decreasing as the field gets weaker. The induced field must point upwards, so the induced current must flow counterclockwise. Our convention says that's positive. This is the only option that starts negative and becomes positive, so it must be option D. All right, our earlier quote-unquote definition of magnetic flux assumed the magnetic field was uniform. It obviously doesn't need to be in the real world, so we need to allow for that case. We'll do our usual trick and invoke calculus. All right, so here we have a field that is increasing in field strength as we go to the right. Not increasing in time, but in space, increases towards the right. And we'll take some small area dA. The flux through that small area would be d phi sub m, which would be b dot dA. B at that location, dot into the area there. And then the total flux, of course, would just be the integral of all of those little things to integrate this entire area. Right, we integrate to get all of them. This is maybe pragmatically difficult, but it is certainly conceptually simple. Let's do an example. Compute the magnetic flux through a rectangular loop with sides capital L and capital W, where the sides of length L are parallel to a long straight wire carrying current capital I, if the nearer side is a distance S from the wire. So this setup. The wire produces a magnetic field which is circular. In the plane of the page on the side of the loop, that field is into the page and has magnitude, remember, which is mu naught I over 2 pi r. Remember that from last chapter, I hope. Of course, since r is changing, b will change over the space of the loop. Notice only when we integrate in x, though, and y there'll be no change. Right, we see b varies only as a function of x, not of y, so we can divide area into strips, each located at a distance x from the wire and of width dx. The flux through the typical strip, the one I have drawn there, is something like d phi sub m, which is b dot dA. But b and dA are in the same direction. We can verify that by saying dA, remember, points perpendicular to the sense of the loop, the plane that contains the loop, and b, we said, was already into the page. So we get BA. So that says that our infinitesimal flux element is now b at evaluated point x times L times dx, because that's the width, that's the area of that little strip, right? An area which is d width, dx wide, and L long. And then we can put in our values, mu naught I over 2 pi r, where r here is now going to be x, so mu naught I over 2 pi x times L dx, which is a bunch of stuff, times dx over x. The stuff being mu naught I L over 2 pi, and then left with dx over x. Then we add up all of the flux through the entire strip, through all the strips that make this thing up, which means we integrate from x equals s to x equals s plus w. And here's the Lagrange algebra. It's really not that bad because integral of dx over x is pretty easy. Since s and s plus w are all positive, I don't need the absolute value bars that are usually there. And so we find that the flux through here is going to be mu naught I L over 2 pi times the natural log of s plus w over s. Is there anything deep in that? No, not particularly, but later on we'll see that if we knew, for instance, if this were moving, we could use this to figure out what kind of current is generated. And that's what happens in the next couple of sections.